Welcome back to another math video. Now in this one we are going to actually do a proof using the Fundamental Theorem of Calculus part 1. So how are we going to start with this? First of all, let's look at the definition. Definition states that if a function f is continuous on the closed interval a to b, then our g of x over here is equal to our capital F of x, which is actually equal to this integral over here. The integral from a to b of f of t with respect to t. And obviously the x within the x or the domain of that function, it lies between the interval a to b. Okay. And here we need our criteria. Okay. So we say that it is continuous. So first of all, yes, we already know it's going to be continuous from a to b in a closed interval, and then differentiable in the open interval a to b, such that g prime of x is equal to f of x. Now, I think that's kind of a lot to take in, but let's kind of break it up a little bit. First of all, our function needs to be continuous in the interval a to b, right? Then we need to show, then we have some function g of x, which is obviously equal to capital F of x, right? We're just correlating those two together, and then we're saying it's equal to some integral with its domain. We can see it where we want to integrate, right? And then obviously we need to see that it's continuous from a to b, differential from a to b in the open interval, and then we can say that therefore g prime of x is equal to f of x. Now first of all, let's kind of look at it like this, right? Let's look at this in more detail. Okay, so I'm going to do this. We're going to say that g of x, right? So let's look at g of x first equals to capital F of x, which I'm using reference to this one right over here. Okay, so we know that g of x is equal to f of x, but if we take the derivative on both sides, like so, with respect to x, we will have g prime of x equals 2, and because we're taking the derivative of capital F of x, it will downgrade to f, small f of x. You could also write it as f prime of x, right, or capital F prime of x, but we normally represent it as small f of x. Okay, great. So now that we kind of have an idea of what we're really going to be doing, essentially what we are going to be doing is we want to actually take the derivative of the integral then. Because remember, we just took the derivative of g of x, meaning we also need to take the derivative of the integral. And that's what our Fundamental Theorem of Calculus says. Part 1 says, so that we will take the derivative of the integral, and then we'll get some other function in terms of our derivative function. Let me explain it in more detail, using reference to our definition of our derivative. Here, we need to recall the definition of a derivative. Now remember, we're going to use the left-hand side to prove that it's equal to the right-hand side. So now we are going to use the definition in terms of g prime of x. And we can see over here that g prime of x is equal to the limit as h approaches 0. Some people use delta x, but we're going to use h for this example. H approaches 0 of, then we're going to write down inside of our parentheses, it's going to be not f, it's going to be g of x plus h, right? Because remember we're working with a function g, minus g of x, it's that difference, all divided by, and we have h, okay? Note that this is kind of a slope equation, the slope formula, or gradient formula, however you want to look at it, where initially we had x plus h minus x, right, in the x-axis, and obviously this one here is the y-axis over here. Okay, so I'm pretty sure if you're not really comfortable with the definition, that's basically what we have. We just have the y, the change in the y over the change in the x, and we take the limit as h approaches 0 for the derivative. Okay, and then obviously the x's will cancel out to give you h, and that's why we use h in our case over here. Okay, cool. Now that we have that idea out of the way, we are going to rewrite this in the following form. So the limit as h approaches 0, because I know people write this on paper, so it's better that we take the 1 over h out. Remember, we take the h from the denominator out, and we can write it as 1 over h multiplied by g of x plus h minus g of x. Okay, and this is equal to g prime of x. Okay, now that we rewrote it like that, what are we going to do? Well, the only thing we can really do is now use reference to a function, or sorry, a sketch or a graph. So let's just do a graph and graph all of this information to do the proper substitutions. Okay, now let's actually sketch the function, right? So let's say that we have some continuous function which looks something like this, right? And we are going to choose the interval. Now remember, it is going to start from a to b. But in this case here, our b is actually represented by whatever is on the x-axis at the end. So we'll have some maximum maximum part of the bound. So let's call some point on the function on our x-axis a, the first point. And then here, we are going to call this point over here the highest part of our bound, which will be, in this case here, x plus h is higher than x, right? Because we're adding some constant, or we're adding something to x. So we are going to call this x plus h, where our x will be represented as something, I don't know. Let's just say that x is here somewhere, okay? Remember, the scale doesn't really matter. Most of the time, you don't even have to draw all of this. This is just a visual representation. So this is some point x that lies between a and x plus h, okay? So here, what do we notice? What we notice is actually the following. We are saying that the function, also we need to represent this function over here as f of t. We're going to call this f of t because remember, that is essentially our integral that we are trying to do the proof with. The function of t with respect to t. But obviously you can see here that we are working with the proper x variables on the x-axis. So here, what are we going to do? We're actually going to do the following. Here, we're going to have the following. We are going to say that g of x plus h and g of x in terms of integrals. And we need to consider, whenever we're working with integrals, the area under the graph, right? Between the x-axis and the curve of the function f of t. So basically, it's going to be our integral from one point to another point, so either x or, we can work with x plus h, of the function of t with respect to t, okay? So in this case, what we're going to do is the following. Our g of x plus h, when we want to represent that as an integral, we are essentially going to be finding the area from, remember, the lowest point, which is a, and we're going to find the area from a until x plus h, meaning we can rewrite this as follows. We can say that g prime of x is equal to the limit as h approaches 0 of 1 over h multiplied by, and we can write this as the integral from a until x plus h, right, of f of t with respect to t. And in this case here, we're minusing it by g of x, according to our definition, g of x, which is going to be this area here. So let me write it in green. So it's going to be g of x, which is basically this whole area from a to x. So we're going to write it as the integral from a until x of f of t with respect to t. And there we go. That's what we have. But now, where are we going to go from here though? Now, this is the difference between two areas, right? The difference between two areas, what did we do? We took the area here from a to x plus h, and we also minus that by the area from a to x, right? So what we are actually left with is this open gap over here between x and x plus h. So therefore, we can actually rewrite this whole thing in terms of that area. So I'm going to try not to move too high up. So let me just move here. There we go. So we can say that g prime of x is equal to the limit as h approaches 0 of 1 over h multiplied by, I can just write this as the integral, or let me just keep the multiplication. This is the integral from x to x plus h, right, of f of t with respect to t, which this is represented by this area over here that we had left from x to x plus h. Okay, cool. Now that we have the understanding like that, we need to consider the following criteria. I want us to just look at this part of the limit. 1 over h times the integral, right? This can actually be represented as the mean value theorem of integration. So the mean value theorem of integration states that if some function, right, f is continuous in the closed interval a to b, then there will exist some c that lies between, the closed interval a to b. So we're saying that the c lies in that bound, okay? So how do we correlate this to that? We need to recall that the mean value theorem is actually has the formula, then f of c, right, such that, I forgot to say, such that f of c is equal to, and then we're going to have, it should be 1 over h multiplied by the integral from a to b of f of x with respect to x, right? That's the definition. And in this case, we can correlate this to this. It's kind of what we have. So let's do that. We are going to now suppose that f of c is equal to 1 over h, right? 1 over h integral from x until x plus h of f of t with respect to t. Note what I just did right there. I manipulated this integral because we can see it in that form. But now we need to also consider the limit as h approaches 0. So let's do that as well. We're going to take the limit on both sides. So it's going to be the limit as h approaches 0 of f of c equals to the limit as h approaches 0 of 1 over h integral from x until x plus h of f of t with respect to t. So now we're actually back to where we kind of had the limit. But now we have something different, which is f of c. But now what we need to consider is the following. Because c actually lies in the interval between a and b, what we need to actually consider is the following. So basically as h approaches 0, right? And because we're referring to this limit, as h approaches 0 and c exists in the interval from x to x plus h, because remember that is basically our bound over here, then therefore what we can actually say is that therefore c will actually approach x, right, which is actually our a value over here. It's our lowest point of the bound. Okay, so what we are saying is that as the limit, so here I'm going to refer it as the limit as h approaches 0 of the function of c, right? This is also the same as saying that c is also approaching x, right? So the limit as c approaches x of f of x. And because we have, f of c. And because the function is continuous, we can therefore do a direct substitution of the limit, saying that f of, so the limit as c approaches x of f of c is also the same as saying f of x. Okay. And now, remember that when we dealt with the mean value theorem of the integral, we actually replaced g prime of x with f of c in our case. We said that this whole thing here, right, was actually the same as the limit as h approaches 0 of f of c, which was actually the same thing as this. So therefore, we can say that this over here, right, the limit as c approaches x of f of c is equal to g prime of x, which is also equal to f of x. Okay, and that is basically the proof using the fundamental theorem of calculus, part 1.